Hello there. Today is the release of Plasticity 2026.1. There are two really exciting new flagship features in this release, but there's also a bunch of smaller hidden gem features that I'm really excited to share with you. So let's get started. Okay, let's start with the new export hidden line command, which creates a 2D vector drawing of your three-dimensional bodies. Now it's called a hidden line drawing because features of the body that are occluded from the given camera angle are typically rendered differently. So for example, this hidden edge is rendered with a dashed line. And another thing that's very common in hidden line drawings is that smoothly connected features, for example, the edges here on this fillet face, which connect U1, are typically rendered in a finer. So what's cool about this is that in addition to the kind of standard orthographic and isometric views, which you might make in another mechanical CAD style program, Plasticity has really foregrounded the aesthetic possibilities of making hidden line drawings. So I'm not going to walk through all of these features, but I'll just focus on a couple that I think are cool. So you can give things a shaded background. So the rasterized image of your 3D viewport will be drawn behind your hidden line drawing. You can, of course, change the thickness of various features like the silhouettes and the hidden lines and so forth. And you can also add different kinds of hatching. There's a lot of creative possibilities that are here. So for example, we can create hatching lines, planar hatching lines on this body and offset them at a certain angle, which you can use to create all sorts of really cool visual effects. Now, in addition to this, and in addition to the kind of standard orthographic and isometric views, you can use the current camera angle. So I'm using this key binding S to capture the screen. And you can even do this in a sort of, or in a literal perspective view, changing, for example, the field of view of the camera, whatever you want to do. And all of these aesthetic possibilities are there for you. So you can use this to create 2D shop drawings. You can use this as an architect to present really compelling, dimensionally accurate renders of your architecture. Okay, next major feature, forgive the choppy editing. I've imported this OBJ file from Blender. It is a polygonal mesh of a monkey head, as you can see. I'm going to run the new Polysplines command. And as you can see, from this control network, from this mesh, it creates a perfectly smooth CAD body. Now, you may be familiar with technologies like subdivision surfaces, sub-D, Catmull Clark from polygonal modeling programs, as well as some CAD programs. Polysplines is a new kind of technology that achieves higher quality surfaces than Catmull Clark. Let me give you a couple examples of how this works. So I'm just going to focus on this area. This is in extraordinary vertex, one of the irregular regions. So it's a vertex with not 4 incident edges. Now this is traditionally a very hard region to achieve tight continuities when converting to a spline surface. I'm going to run the measure continuity command, and you can see that we have 0 deviation G0, 0 deviation G1, and 0 deviation G2. So a very cool feature of polysplines is that when converted to spline surfaces, you have exact G2 continuity everywhere in the regular and the irregular regions. Now, perhaps more importantly, the actual generated surfaces in the regular regions are degree 3 bicubic surfaces, and in the irregular regions, they're degree 6 with 6 spans surfaces. So they are the simplest surfaces on the market at any price point of any CAD product when producing this level of continuity. And that's really important because the simplicity of these surfaces means that the reflection lines are going to be better, and the downstream modeling experience, meaning any kinds of booleans and fillets we do on top of this body, are going to be more accurate and more robust. Okay, permit me to nerd out on this a little bit. Here I am in Blender, by the way. I have a simple cube with a subdivision surface modifier. Now, even a simple cube has irregular regions. It has an EV, an extraordinary vertex right here. So here's a vertex with 3 incident edges. Okay, so I have here on the left one way of converting that Catmull-Clark subdivision surface cube into a CAD body. And on the right, we have the Polysplines approach. Polysplines has fewer faces, which is definitely better and more robust at downstream modeling. But I want to focus now on the quality of the highlights. Okay, so I'm going to put on the reflection lines. You can see that at a rough glance, they look very similar, but there are some notable differences. And let's use some curvature combs and deviation plots to show those differences. Now, this conversion approach achieves G2, not quite with the tolerances of polysplines, but what I want to focus on is how jagged this curvature comb is. This is not a fault of the conversion, this is a fault of Catmull-Clark itself. The true limit surface of Catmull-Clark has relatively frequent and rapid changes in like the sign of the derivative of the curvature. And you can see that compared to the very smooth and calm variation of the polyspline surface, there is this kind of, relatively speaking, jagged curvature cone. So just to make this like a little bit clearer, if we zoom in here, in the irregular region right here, you can see that there's just a kind of stiffness in the way that the reflection line moves over what is the irregular region. So the irregular region's right here, right? And you can just see that there's a kind of rapid change in the curvature. It's you know, is this that big of a deal? I don't know. But it's much stiffer than the perfectly smooth polyspline version. All right, let me show you how I intend people to use polysplines. It's not by importing OBJ files. Okay, so I've used the Blender Bridge add-on. Note the version 2.2 and above is going to have polysplines, and again, you have to have Studio for this to work. There's now an outbox and an inbox, so you can send information out via the outbox. Now, for now, the only information that you can send out are things with a subdivision surface modifier at the bottom of the stack. So you can use other array, mirror, whatever modifiers too. And then once it's in the outbox and you click refresh, it will magically transport from Blender into Plasticity. And what that allows you to do is create a Catmull-Clark mesh in Blender and a Polysplines body in Plasticity relatively rapidly. Okay, so one disadvantage of this is that you have to use 2 programs to bring sophisticated Polysplines bodies into Plasticity. But it's actually, in a certain way, a big advantage for us. Because if you look at the market right now of CAD programs with mesh modeling environments for subdivision surfaces, this can be Alias, this can be Rhino, this can be the forms environment for T-splines in Fusion, they are all, relatively speaking, mediocre mesh modeling environments relative to Blender, 3ds Max, etc. It takes years to build robust mesh modeling tools, and even after all these years, you can look at what the CAD programs are doing, and none of them have the tools like loop tools, the modifiers, just the fluidity of modeling of Blender. So this is a weakness that we don't have these tools directly in Plasticity, but it's also a strength that our tight integration of Blender allows, I think, much more rapid and productive mesh modeling, control network modeling. Well, up to you to decide. Okay, we're done nerding out for the moment. Now I want to transition to some of the minor features in this release. There are dozens of minor features, as usual, but there are 3 that I really want to call attention to, like 3 top tips for using Plasticity in 2026. Okay, let's get started. I'm just gonna create a simple scene here. Let's maybe make another cube. Okay, so people who are coming to Plasticity from more traditional mechanical CAD style programs often find the 3D sketching environment of Plasticity somewhat confusing. So I just drew a spline, and you can see that this spline is 3-dimensional. It's not planar, it's not 2-dimensional, okay? And even in an orthogonal view, when sketching, like let me draw here this little circle. I'll do this one more time. I'll do this here. You can see that while these circles are coplanar, they're not on exactly the same plane because I drew them on this body and on that body in my first click. Now, Plasticity 2026 has a new feature called 2D snapping. And 2D snapping means that anytime you're in any kind of orthogonal view or with a construction plane, everything you draw will be fully projected onto that plane. Okay, so I'm just making a bunch of circles here and blah, blah, blah. I'm making a spline. Okay, all of these are totally coplanar now, not just parallel. So that's going to be true in like an orthogonal view, like the right view, or in an explicit construction plane. Now, when you have an explicit construction plane, anytime you have an explicit construction plane, it acts as a kind of 2D sketch, and all drawing is on that. So if you're working from precise drawings or you're more used to mechanical CAD style modeling, you will almost certainly find this feature very helpful. Okay, next. This is a bit more of a pro tip than a cool feature. One of the key bindings in Plasticity has changed. This is a bit boring, but I think it's worth calling out. Normally, to make a symmetric extrude, you would hit Tab, okay? But now it's S for symmetric to extrude in two directions. Now, the motivation behind that is that now any kind of 3D gizmo, in addition to the usual key bindings like X1 for moving 1 meter, you can now tab into these gizmos. So I'm tabbing into Y, tabbing into Z, and tab now means universally in Plasticity, move to the next input field, whether that's in a dialog or in a gizmo with multiple kinds of input. And so key bindings that were tab before, which usually it's like it was meant for symmetrical things, have generally migrated to S for symmetrical or lock distances, or however you want to call it. Okay, last feature. I'm going to create a group. Okay, so the sphere is in the group. Let me create another sphere. And you'll see that this other sphere I created is in the root scene. Now, a new feature in Plasticity 2026 is that if you double click on a group, you see the color change to purple. That group becomes the active group. And that means all newly created bodies will be in that group. If you're familiar with Blender, this should be right at home, although it's a double click and not a single click. And what's super compelling about that is if I make an instance of a group, for example, which I just did, and let me I don't know, let's say -y minus 1. I'll just make a mirror of this, okay? Let me delete this sphere, it's a bit confusing. Now, if this group is active and there's a mirror instance of the group, everything that I create will be mirrored automatically, right? And so this is just one example of how using active groups with instances can be cool, but active groups, useful feature. Pro tip, keep it in mind for your future modeling experience. All right, thanks everybody. Enjoy Plasticity 2026 and have a nice weekend.